Hello, 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 everybody. You love to see it. You love to see it. I missed Yusuf. I missed the game because I didn't get the notice for it. Oh man, I need to get the push notifications because my timings are all off. So I gotta watch the replay of the game. But if it's a 1-0 win, I'll take a 1-0 win for the tags any day, any day. I want to watch that replay, Yusuf. Good afternoon, everybody. Hisa, good afternoon. Pistache, good afternoon. Hello, everybody. Absolutely fantastic to see you all. Angie, good afternoon. How's everybody? I hope everybody had an absolutely great weekend. Hopefully everybody's doing very, very well. Oh, we had a nice time this weekend. 100%. All right. Today, as you can tell, I have a microphone this time. So I'm no longer using the headset microphone here. I actually have the I've got a Yeti microphone. So hopefully this I'll sound a little bit better over the thing, and then hopefully it works out pretty decent. So yeah, that's what I did. All right. In any case, we are. In any case, hopefully, again, if things are a little loud or things are a little bit too soft, just let me know, and we'll hopefully just work something out. That's fine. All right. In any case, everybody, we need to get started here, ladies and gentlemen. We'll have people start to come and trickle in here. Started a bit behind, but that's not a problem here. Very good. A hard-fought victory. Good. Who scored the goal there, Yusuf? Yusuf, I have to know who scored the goal. It was, I'm pretty sure Devs is very happy about that, by the way. I'm gonna rewatch the game and then I'll tell you what I thought. Okay, ladies and gentlemen, we're gonna do some intros here. We're gonna get started here with section 5.5 and 5.6. And we will get the ball rolling here. So, again, we'll get, yeah, let's do it. All right, let's go. Okay, let's get started today. Welcome back to a Tuesday. All right, hopefully you have a nice weekend. All right, so for today, we're going to continue on here. Street Skiller, thank you so much for the follow. I appreciate you. So for today, everybody, we're going to go ahead and get started here with section 5.5. We're going to talk about, talking about counting here today, okay? So that's the primary focus of what we're going to be talking about is counting, and of course, figuring out probabilities around the idea of counting. All right, Chris Newby from the penalty spot. That's legit, man. That's a lot of respect. Noobs is pretty good on the penalty spot there. He's very good. Okay. Chris Newby is a class act. All right. So let's go to the big board here, and let's see exactly what we're working with. Buddy, badoo. All right. So let's talk about what we're going to be discussing here today. Today we're going to be talking about counting using the multiplication rule. We're going to be talking about permutations, combinations, solving using permutations with non-distinct items. If we get to that, should be able to get to that, and compute some probabilities as well. All right, so let's talk about counting here in general. Okay, now counting, of course, when we talk about counting in mathematics, counting can be one thing in math. For example, counting 1, 2, 3, 4, 5. That's all well and good, but specifically what we are trying to find is we're not just counting 1, 2, 3, 4, and 5 here. What we actually want to talk about here is how many ways we can do a certain something here, depending on the context of the problem. Okay, so the first thing that we're going to talk about here, and we'll look at an example here to showcase exactly how counting works, is let's look at number one here. What is the fundamental principle of counting? And this is where this multiplication rule is going to come into play. And that is, if a task, if some kind of task, okay, consists of a sequence of choices in which there are P selections for the first choice, Q selections for the second choice, R selections for the third choice, and so on, then the number of ways that the task can be done is P times Q times R times dot 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 number of ways. Okay, so that is essentially what the fundamental principle of counting is talking about. Now, to put it into context here, that make sure that this is a little abstract, admittingly, but let's take a good look here at a practical example. And we're just going to do a simple paint tool here. We don't actually need the book for this part, at least. We'll look at some book problems, though, today. Okay, so let's do a quick example here. So let's say, for example, you're going to go get some ice cream. Okay, so you're going to go get some ice cream. All right, so you go to the ice cream shop. You're like, I want an ice cream cone or ice cream scoops. And you're like, okay, you want an ice cream that has 3 flavors. All right, so you want 3 flavors, 3 scoops of ice cream. And you need 3 separate flavors. All right, so they all have to be different flavors. You can't have the same flavor. All right, so they have to be different. Okay, now saying that they're different, that's fine. All right, now let's see. Let's say we're in a shop, and this shop here has 20 different flavors. So let's say it has 20 flavors of ice cream that you get to select from, and you're picking 3 different ones. Okay, now let's figure out how many ways we can have our different ice cream cones or ice cream, buckets or whatever. Whatever you want to call it. All right. So let's look at the first scoop, the second scoop, and the third scoop. Okay, now, let's ask this question here. For the first scoop of ice cream, how many choices of flavors do I have for the first scoop of ice cream that I want? How many choices do I have for the first scoop of ice cream, according to this scenario here? Okay, that's correct. I have 20 choices, because again, I have 20 different flavors, right? So I have 20 possible choices for the first group. Okay. So you can pick any flavor that you want, your favorite one maybe. Maybe you're like me, you like mint chocolate chip, or maybe vanilla. I don't know. Those are my 2 favorite flavors. But maybe you pick one of those, and then if you have multiple favorite flavors, then you pick one of those, and that'll be your first scoop. Okay, so your first scoop is down. Person asks, what do you want for your second scoop? Okay, what about the second scoop here? How many choices do we have for the second scoop of ice cream? All right, so we have 19 possible flavors, right? That's right. We have 19 possible choices. We can't repeat the same flavors before. Sounds great, but, we're not given that option here. They have to be 3 different scoops. Fair enough. Easy peasy. All right, so we have 19 different flavors. So again, we just removed 1 out of the pool. We have 19 left over. How about the third one here? The third scoop here. How many possible flavors can we select from after that? 18. Okay. Very good. So 18 is correct. All right. So we have 18 possibilities to select the third scoop here, just like so. All right. So if we're trying to figure out how many possible ice cream cones that we can have for 3 scoops of different varieties at the very least, we're just going to take 20 multiplied by 19 multiplied by 18. Okay? And does anybody have an answer for me here? We have 20 multiplied by 19 multiplied by 18. What do we get here? $68.40. Okay, $68.40. All right. Nah, it's okay, Horitz. No problem. Yeah, just a mistake with the keys. Alright, so 6,840. So there's 6,840 possible ice cream cones that we can make underneath having 20 flavors and 3 different scoops. Alright, seems fair. Alright, any questions about that so far? Any questions? So hopefully that's not too bad. Again, what I want you to recognize here is that you just basically logicked it out. Okay, you just basically used logic to figure out how many possible ways we can make ice cream cones based on the current context of the problem. So again, just common sense at the end of the day in order to actually construct this and put it together. Now, let's take a look at something slightly a bit different, but actually one and the same. You'll understand what I mean by that. But for us to do that here, we do need a little bit of build-up. Let's take a look at number 2 on the handout here, and you'll see what I'm talking about here momentarily. All right, so number 2 says, what is factorial and its notation? Now, this is something we're going to be talking about here, especially in the context of talking about permutations and combinations. Now, factorial's notation is exactly listed as on the sheet here. It is the exclamation point, so that is not a typo, as actually the notation in mathematics for factorial is the exclamation point. So n factorial here is n times n minus 1 times n minus 2 times dot 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 times 3 times 2 times 1. So they're always whole numbers, positive whole numbers. And you go all the way down from that positive whole number, multiply every number all the way down to 1. So as you see there on the bottom, 5 factorial is 5 times 4 times 3 times 2 times 1. Multiply all those numbers together. In this case, you get 120. And then we also have the special property here of factorials, where 0 factorial is equal to 1. That's pretty much often used in certain circumstances, so it's not like it's a very special thing, of course, but again, you do see that pop up from time to time. You know that 0 factorial will be equal to 1. Just one of those weird properties, and we're just going to pretty much use it. All right, now why are these factorials here in particular very important? Well, for the next couple of things that we're going to be talking about here, we're going to be talking about, first of all, let's talk about the first one here, which is talking about permutations. So question number 3 says, what is a permutation? All right. So a permutation here is the number of arrangements of r things chosen from a pool of n things where order matters. Now you can see the notation here. The notation here is npr, okay? And that's equal to n factorial over n minus r factorial. And again, repetition is not allowed. Now, let me point this out here. Why is this really important here? Well, let's go back to our example for just a moment. We had an ice cream here of 3 flavors that we had to select from. But the most important part here is that every flavor had to be different in order for us to get to this result here. In fact, this example that we did here for ice cream is a prime example for permutations. Now, the reason why this is a permutation type of example is because order definitely matters. Once we select the first flavor, like let's say the first flavor, for example, was cookie dough, all right? Well, I cannot get another scoop of cookie dough. I get 1 scoop of cookie dough, and that's it. That's all I get. Okay, so I'm not allowed to select cookie dough, that particular flavor, again, for my other 2 scoops. So order does significantly matter here for the next scoop. All right, now, if we were to do it using this same scenario here, I had 20 flavors of ice cream, and I permute them 3 times. So it's like 20p3, for example. And if I were to do this out, I would have 20 factorial over 20 minus 3 factorial. So if I were to do this by hand, you'll see what happens here. Here I get 20 factorial, which is, again, you'll have 20 factorial divided by 17 factorial. And I'll show you what happens here with this particular process. 20 factorial can be written as 20 times 19 times 18 times 17. Now, we could go all the way down to 1, but another way to write this is we could just write 17 factorial, because that's 17 times 16 all the way down to 1. And we could divide that by 17 factorial. And basically what will happen is these will cancel out. Thus, as you see here, that leaves us with the 20 times 19 times 18 that we had talked about from before, where we just kind of logicked it out and be able to find our final answer of 6840. So this is just another way to get to that same result, and just understanding that order does matter. So if we're looking at a situation where order matters, hey, guess what? We're going to use this formula, and we're going to go ahead and solve for that particular problem. All right. Now, let's take a look at another example here. Ice cream example is simple and all, but let's look at number 47 here. It's the example that I would like to use. So this is in the book here. So let's use that here. Okay. Hang on a second. All right. Alrighty. So 47. Let's go ahead and read this off together, and let's see how we can work this out. All right. Forming a committee. 4 members from a 20-person committee are to be selected randomly to serve as a chairperson, vice chairperson, secretary, and treasurer. The first person selected is the chairperson, the second the vice chair, the third the secretary, and the fourth the treasurer. How many different leadership structures are possible? Okay, now let me ask you this question here, everyone, and that is, does order matter here for number 47? Does order matter for number 47? Yes or no? Does order matter here for number 47? So simple yes or no, yes, okay. And why would, so the question, I guess, after that is, if order matters, why does it matter? No? Let me go ahead and answer this question here. Does order matter here for number 47 in this chairperson, chair committee, just a random committee, I should say. In this case here, the answer is, because it states that the first person selected is going to be the chairperson. That is correct. Okay, so in this case here, order does matter by a significant amount. And it's exactly as Anna has stated here. If the first person that's selected is the chairperson, well, then that person is already slotted into one particular job, okay? That person is already in the committee, and that's their position, is chairperson. So a person cannot be chairperson and be vice chairperson and be secretary and be treasurer. Okay, that's not possible. Okay, once that first person is selected, that's it. They only get that one position, and they cannot qualify for any of the other positions on the committee. Okay, so I'm just going to go ahead and just say, yes, order does matter here. Now, the real question is, how do we go ahead and solve for how many committees that we can make? How many different structures, leadership structures that we can make here in this case? How many different leadership structures can we make here? What could we use here in this instance? What do you guys think? How should we find the number of leadership structures? What do you guys think? What do I have to use here, guys? Don't worry, I can wait. It's fine. You guys gotta tell me, though. Okay, that's correct. Very good, Horitz. That's right. We're gonna use permutations. We're gonna use permutations. Alright, and if we look at the problem here appropriately, we are indeed going to have 20 people here. So 20 permute 4. Alright. 5, I totally understand. No problem. I know the next one is 50. That's okay. We're going to have 20 factorial over 20 minus 4 factorial. So we're going to have 20... Again, 20 times 19 times 18 times 17 times 16 factorial over 16 factorial. Again, you can pretty much logic this out if you like. You'll have 20 times 19 times 18 times 17. Pretty much similar to the ice cream problem here. And then, what do we get here in this instance? What's 20 times 19 times 18 times 17? What do we get there? What's our final answer for this? 20 times 19 times 18 times 17. You guys got your calculators out. You guys are going to want to take your calculators out. So, just to let you know. Uh, 116,280. Alright? Good. Alright, good beats. Alright, any questions about that so far? Any questions? Alright. Okay. No? Alright. So if you have your calculator out, I'm going to do part of the calculator portion of the program. Alright, if you have your calculator out, please type done in the chat. Please type done in the chat if you have your calculator out. We're going to go over a calculator portion of the program here. Just want to be sure everybody's got that in their calculators here. Alright. Okay, so, alright. She almost got it. Okay, good. Okay, alright. So, you guys know what answer that we got here. So, through the formula here, we got 116,280. Now, what we're going to be doing here next is we're going to be replicating that here via the calculator as well. This process that I'm going to show you here works for both the old school and new school calculator, so it doesn't matter which way, which calculator and software that you got. You're going to be doing the same button presses irrespective. Alright, so the first thing that we're going to do is we want to figure out 20p4 here on the calculator. That's what we're going to figure out, this 20 permute 4. So what I would like you to do here first is type in the number 20. So just type in the number 20 on the main screen. That's not a problem here. Alright, now once you went ahead and typed out number 20, I'm going to go ahead and type this in chat here. You're going to go hit the math key and then go to the PROB menu here. So this is, we're going to hit the math key here. And if you see that submenu up top, you're just going to scroll over to that guy right there, which just says PROB. Now, the option that you want to choose here is you're going to select option number 2. You says, notice it has the exact notation here, which was NPR. So select option 2, which is NPR. All right. And we'll go ahead and hit enter on that. Now, it may format it like this, where it has a small 20. That's perfectly fine. If you have the newer style calculator, it'll look like this. If you have the old style calculator, you're going to see that it kind of looks like this, like 20, and then it literally has NPR next to it, and then you'll put the number 4 next to that. So you're going to put, for the old style calculator, it looks slightly different, but really is the same meaning. We'll have something akin to that. All right, and then go ahead and hit enter, and notice that we get the same exact answer here of 116,280. Okay, so again, type done in the chat if you got this exact answer there. Then try again, Juan. Yours should not say error. That means you might have done it backwards. You have to put in 20 first. So remember, type in 21. That's the first thing you have to do. And then hit the math key. Go to PROB. Select number 2. And then hit 4. And then hit enter on your calculator. And you should get the same thing here. Make sure you have that on the main screen there, Juan. Got it? Perfect. All right, good stuff. Okay, so you'll notice that we took a little bit of a shortcut there to get the permutations. Again, the key thing here in these problems is to first recognize that we're going to use permutations if order matters as part of that problem. Okay, so I'm just going to point that out there. That will be important. Okay, very good. And we're going to come back and use the calculator here, so no worries, we're going to use that here in the next example as well. All right, so there you go. All right, any questions about that so far? All right, so we've talked about permutations here. Now let's talk about the other half, the kind of complement to permutations. Let's look at that guy. All right, and that's here in the next question here on the handout. Let's look at question number 4. Question 4 says, what is a combination? What is a combination here? So a combination here is the number of, the formal definition here, the number of arrangements of R things chosen from a pool of N things where order does not matter. So order does not matter here. Okay, so if you notice here, we have the notation here is NCR, and if you saw carefully on the calculator, it was there right underneath NPR. So we're going to come back to that calculation here. I'll use that in the calculator momentarily. But NCR here is equivalent to n factorial divided by r factorial times n minus r factorial. And since order doesn't matter here, we do not want repetition to be allowed. And I'm probably thinking, hold on a second. What do you mean by that? What do you mean by repetition not allowed? How do you justify that something is a combination? Okay, let's take a look at a practical example, an everyday example, and we'll see exactly why this is equally as important, if not more so. All right, so let me ask let's put up a poll here. Why not? Let's do a poll. All right. Put up a new poll. Let's put up a quick poll here. There we are. So have you ever played the Lotto? Have you ever played the Lotto? All right, so if you've ever bought a Powerball ticket, or an instant scratcher or something like that. Maybe you've been to the gas station or the grocery store, maybe pick something up here, and that's fine. If you've never played the lotto, that's not a big deal either, right? But again, maybe you're like, oh my gosh, there's a lot of money in the lotto, you know, like $500 million. You're like, oh well, I gotta play, ha 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 ha, you know. I played the lotto before, so only when the jackpots are really big. So I'm just getting a gauge about how many people have played the lotto before. So for some people, what I'll say here next is nothing brand new. But okay, so a little over half of the people have played lotto before. Now let's talk about lotto here. Now specifically, in this example, we're going to talk about Powerball. All right. Now, Powerball is a game here that's, again, a lotto. There's several different types of lotto games I think you've probably heard of here. Powerball, maybe one of them you probably have heard of in the news. If you've never played lotto before, you've probably heard of Powerball. Again, Powerball is what's the thing here? So, just gonna bring this up on screen. So it has a jackpot of $570 million. Okay, so there you go. But of course, the odds of you winning the Powerball here are pretty difficult. And what we're going to find out here in this example is actually computing the odds or finding how many ways you can get certain things here, combinations of Powerball numbers to appear. And again, we can also figure out the probability of winning the grand prize here, also in the Powerball. All right, so that's what we're going to do. Now let's talk about the rules, because the rules here are most important. Now, underneath the Powerball rules, the way it works is that there's going to be 5 white balls, okay? So there's 5 white balls. And these 5 white balls have to be numbered between, are going to be numbered between 1 to 69. Right? Very nice. All right, now, then there is the Powerball. Now, the Powerball here is 1 to 26. Okay, so there's 26 numbers here for the Powerball. However, the Powerball is separate than that of the first 5 white balls. Okay, so that's pretty much how it's going to work. Now, here's a question for you. Let's say when you do any drawing, okay, of any variety, you know, you can be as simple as possible. Kate, thank you for the follow. Appreciate that. When you do a drawing of any variety, okay, you spin the drum of balls, okay, there's 69 balls in this drum. Okay, you pull out 5 of them. And let's say those balls here happen to be, you know, let's say we have the numbers on our ticket here, 1, 2, 3, 4, 5. Okay, and the balls come out, you know, 2, 1, 3, 5, 4, or could come out 3, 1, 5, 4, 2. And then make stuff up. 2, 5, 3. All right. So let me ask a question here. If I look at these set of 4 numbers that you see here, all right, are these the same? Are these the same? Is 1, 2, 3, 4, 5 the same as 2, 1, 3, 5, 4? The same as 3, 1, 5, 4, 2? The same as 2, 5, 4, 3, 1? Are those the same? Yes or no? All right, Hort says no. But if these are the numbers that came out of the drum, all right, just to, you know, these are the winning, let's say these are the winning numbers that came out of the drum. Let's say, you know, in separate pulls. Are these the same? Are all 4 of these the same? The answer, no. So is 1, 2, 3, 4, 5, 1 the same as 2, 1, 3, 5, 4? So if you pulled 5 balls out of a bucket of 69 balls, for example, and you pulled it out, and you said, hey, I got 1, I got 2, I got 3, I got 4, I got 5, is that the same as me doing a separate pull and I pulled out a 2, a 1, a 5, a 3, a 5, and a 4? Are those the same in a game of Lotto? That's the real question here. I guess a better way to put this is, let me show you at least this. I know I can bring this up. Here's an image of a Powerball ticket. So if you haven't seen one before or never really played the Lotto, which is fine, it's no big deal. Okay, so here's an example here on the left of an example of a Powerball ticket of some variety. Are these 4 sets of numbers, would they be considered the same? Or would they be different? That's really the question here. So yes or no? What do you guys think? Maybe make up a new poll if you're not sure. Go ahead and put your answers there in the poll. I'll put up a short poll here. Yes or no, are they the same? You just pick one, that's fine. Well, that's what's for you to determine there, Juan. So you're gonna pick either yes or no. Do you think order matters or does order does not matter? That's the real question here. That's a good observation. I got a few more seconds here. Alright, so everybody said no, they are not the same. Alright, let's talk about the answer here. What is the answer here? Is it yes or is it no? The answer is that, in fact, yes, they are the same. Let me use this here. You're probably saying, hold up a second. Everybody said it was no, but you're telling me, yeah? I'm like, yeah, I am actually. I'm telling you that everybody was wrong. Alright? But let me explain exactly why that happens to be the case here. Okay. So let's say you're holding this ticket here, this Powerball ticket, right? And, you know, the drawing comes. The drawing comes in the bucket, the balls that land out of the bucket are 1, 2, 3, 4, and 5. Now take a look here at this ticket. Notice this ticket here is written in numerical order. Okay? So you just have to compare. Do I have a 1 on my ticket? Yes. Do I have a 2 on my ticket? Yes. Do I have a 3? Yes. Do I have a 4? Yes. Do I have a 5? Yes. So I've matched all 5 numbers. 1, 2, 3, 4, and 5. Now that's written in numerical order on my ticket. However, if I look at the second one here, let's say the first ball that comes out from the drawing is 2. Do I have a 2 on my ticket? Well, the answer is still yes. Because even if these are written in numerical order, I'm just, at the end of the day in a Lotto, I'm just trying to match the numbers. Right? I'm just trying to match the numbers. So if I have a 2 on my ticket, that's good. If I have a 1 on my ticket, that's good. If I have a 3 on my ticket, that's good too. If I have a 5 on my ticket, great. If I have a 4 on my ticket, okay. So I've effectively matched all 5 numbers here. The same exact 5 numbers of 1, 2, 3, 4, and 5. So in this case here, when it comes to the lottery, is that order does not matter for winning numbers in the Lotto. Okay? Order does not matter for winning numbers in the Lotto. All you're trying to do is match up what your numbers on your ticket is to whatever the balls fall. However the balls may fall, you're just trying to match them up. No matter what order it comes out, as long as they match up, you're a winner. That's how it works. Does everybody... Are there any questions about that so far? I'll let that digest for a second here. Now, there is a matter of consequence here for this. Can multiple people win the lotto? Yes. Multiple people can win the lotto as long as they have the same combination, right? So let's say one person had 1, 2, 3, 4, 5 and the right Powerball, and you have 1, 2, 3, 4, 5 and the right Powerball. Okay, multiple people can certainly win the Powerball. That's why order does not matter. It's not limited to, again, you take a look at the ticket here, especially the picture of the ticket that it's on the screen. Notice that every single line of the numbers here are all in numerical order, right? Aren't they all in numerical order? Every single one? Right? So again, you don't have to write in numerical order. If order mattered, it would be stated in the game, but it's not. So order doesn't matter here when it comes to lotto. All right. Now, because of this fact here, because order does not matter, the biggest, what's the big kind of reasoning behind this here? Why is this important? The reason why, again, now that we know that order doesn't matter here, and because 1, 2, 3, 4, 5 and 2, 1, 3, 5, 4 and all these other dudes are the same thing, we do not want to count these other three. Once we count 1, 2, 3, 4, 5, any other permutations of 1, 2, 3, 4, 5, any other ways we can write 1, 2, 3, 4, 5, we don't want to count those. We should only count that one time. So we don't want to repeat another telling of 1, 2, 3, 4, 5 at the end of the day. And that's why we have this extra r factorial, is to take away these repetitions at the end of the day. Okay? So what does that mean here? That means that, in effect, if we're going to find the 5 white balls, the number of ways we can draw 5 white balls, and order does not matter, we're going to use the number of combinations here in order to do so. Now, the way we do that here is we have 69 balls, and we choose 5 of them. Okay? So we have 69, choose 5. And we have 26 Powerballs. Again, that's going to be a separate thing. So we have 69 choose 5 times 26 to figuring out how many combinations of numbers that we can have in the Powerball. So we're going to do this together here on the calculator. I'll rewrite it down here. Let's put it on the calculator here. Let's see what we're working with. We have 69. Again, we're going to put 69 here. Hit the math key. Now this time here, we're going to go to PROB, but we're not going to pick number 2. I want you to pick number 3, which says NCR. So same process here, and then we'll pick NCR this time. And we have 69 choose 5. Remember to hit the right arrow key here so you can get to this main line. And then times 26 for the Powerballs. And as we can see here, we have 292,201,338 possible combinations of numbers, of sets of numbers in the Powerball. So our chances to win is going to be 1 out of 292,201,338, which is a very low percentage, by the way. A extremely low percentage. Are there any questions about that? Any questions so far about that? You can see how things kind of work in a reality-based kind of situation when using the lotto as a good backdrop for that. All right, let's take a good look here at a few more examples here for sure. So need to practice just a little bit more, and we'll see exactly how things work out. Okay. All right, we'll get to that part here. Yeah, we'll get to that a little later. This. Hang on a second, I got too many windows open. All right, this wasn't here. A second, close. Where is it? Here it is. Okay, I was looking for the book here. All right, there we are. Okay. Okay, so let's look at another one here. All right, so let's look at. All right, here we go. Let's look at number 53. Okay, so let's look at 53 here. Do that one together. So a quick problem here. 53. Children. A family has 6 children. If this family has exactly 2 boys, how many different birth and gender orders are possible? Okay, so a family has 6 children. Family has exactly 2 boys. How many different birth and gender orders are possible? Okay. So again, you could have, say 4 girls and 2 boys. Okay, for example, in that order, you could have again 1 boy followed by 4 girls, and the last one could be a boy. Whatever the case may be. Again, in this case here, let's talk about this. All right, so the question about 53 is, does order matter? Does order matter in this instance? We have 2 boys, 4 girls, 6 children. Yeah, order does not matter here. Oh, yeah, order matters? So we just care about birth and gender orders. So we don't care about age or nothing. That's not what. So again, you have to understand that the first person in line could be a boy or girl, but in this case, yeah. So again, understand, if there's a different qualifier, then I wouldn't be hesitant to agree with you there, Horitz. But order doesn't matter here, since we only care about the birth and gender orders here. Okay, so it could be girl, boy, girl, boy, girl, girl. Fine, whatever. Okay, it could be whatever you want at the end of the day. Okay, so let's figure out how many ways we can actually have that happen. Well, all right. So the way we could do this is, if we have 6 kids, we have 6 choose. Oops, sorry. We're gonna have 6 choose 2. Okay, so we're gonna do 6 choose 2 at the end of the day. And if you do 6 choose 2 on the calculator, what do you get? What's 6 choose 2 going to be? That's the way we're going to do this here. 6 choose 2 for the 2 boys. And then we'll assume that the rest are girls. What's 6 choose 2 equal to? Right, 15. 15 is correct. Good, good. All right. So 15 ways to go ahead and put that in order. All right, that seems fair. No problem. All right. Any questions so far about that? Any questions? All right. Let's go ahead and pick another one here. All right. There's another Mega Millions one. That's fine. All right. Now, the next one here I'm going to do is number 61. And now we're going to get into the kind of the probability aspect of things and kind of compare a couple things. So let's take a look at this here. Okay, so number 61, selecting a jury. The grade appeal process in a university requires that a judge be structured by selecting 5 individuals randomly from a pool of 8 students and 10 faculty. What is the probability of selecting a jury of all students? Okay, so let's take stock in what we have here before we even start the probability process, okay? First and foremost here, we have a pool of people, all right? So we have 10 faculty here. So we have 10 faculty and 8 students, okay? So we got here. Now, the jury here in this case has to be 5 individuals, okay? So out of these pool of people, the jury has to be 5 people. Again, it could be a mix, it could be everyone, we don't know, but again, that's what these scenarios are going to give us here, is exactly what the makeup of each jury is going to be. So in letter A, what they're asking us to find is the probability is if everybody that we pick are students, so they're all students. Now remember here, one of the most important parts in this case is that order in this case doesn't matter. If I have Bob, Mary, Sue, and 2 other people, well, that's the same as Mary, Sue, and Bob and those 2 other people. Okay, so there's no difference in this case. Again, it's the same committee of people that is going to make up the jury selection at the end of the day. Now, if they're all students here, how can we find the number of combinations of an all-student jury? What can we do here? It's the number of combinations here for an all-student jury. So this is going to be combinations. A number of combinations. An all-student jury. The number of combinations of an all-student jury. Anybody write that in the chat there? I'll wait. Number of combinations of an all-student jury. How many students do we have, guys? How many students do we have? Let's answer that question. How many students do we have? 8? Okay, so we got 8 students. How many students are we picking out of those 8? How many are we choosing? We go 8, choose. How many are we choosing here, guys? So, you would say, if we're picking out the number of combos for an all-student jury, it would be 8, choose 5. So 8, choose, you're choosing 5. Okay. Are there any questions about that? 8, choose 5. Now, second question here is we want to find the total number of combinations. That is indeed 6720. Okay. We'll get to that here in just a second, Horace. We're gonna see the bottom part here as well. So the total number of combinations. Well, how many people do we have total overall that we're selecting of? What's the total pool of people in this problem? How many people total do we have overall in this pool? 5? No. We're selecting 5 people here, Anna. But how many people total in the pool between faculty and students? So I just need you to get the right perspective here. I'm selecting 5. This is true. 18. That's right. So if I have 18, I'm going to have 18. So the total number of combinations here, I have 18 people in the pool, and I'm choosing 5 of them. And this is if I had chosen 5 people at random, you know, and then say, okay, hey, how many combinations of choosing 5 people at random for whatever? Okay, now on the calculator here, this is what we're going to do. We're going to do 8 choose 5. Now you can do this as separate things, because I know some of you put 56, and that's perfectly cool. Alright, but if we put it in the calculator here, we'll be able to do this at once. So we could do 8, math key, PROB, NCR, put the 5 there, hit the right arrow, put the parenthesis, divided by, and parentheses here, 18, math key here, PROB, go to NCR, 18 choose 5, hit that right arrow, and close the parenthesis. And then we'll hit enter. Okay, and so as we can see here, we get 0.0065. What I would like you to do next is, if you got this same exact answer here, please type done in the chat if you got this same exact answer on your calculator. I want to be sure everybody was able to replicate what I did. Type done in the chat if you got this to work out on your calculator. Hopefully people are not having too much trouble. Okay. Alright, so that, my friends, is letter A. That, my friends, is letter A. Let's work on letter B. Alright. Good. Okay. Okay, so let's see if you guys can put this together now that you have a good idea how to do letter A. Letter B, hopefully, will be a bit easier. What's the probability that you select a jury of all faculty? So all 5 people are all faculty. How would you set up this particular probability? Anybody tell me here? Let's do the top part here first. What's the number of combinations, in this case, to select all faculty? How would we set that up? All faculty case. So all faculty here. What's the number of combinations to select all faculty, folks? All right. Okay, here we go. All right. First one's always a tough one. Just hoping that you guys could pick up on that. Very good. That is correct. Okay, so 10 choose 5 is absolutely spot on. Very good, everybody. Very good. All right. Excellent. Now, the number of ways we can have total number of combinations here is the same. 18 choose 5. That's correct, Horace. All right. So we're going to have 10 choose 5 divided by, exactly as Horitz has stated here, 18 choose 5, still the total number of combinations here in our given scenario. Okay, does anybody got an answer for me here? In this case, what's our decimal equivalent here? 10 choose 5 divided by 18 choose 5. What's our final answer for this? 0.0294. Okay. Okay. Good stuff. All right. So far, so bueno. All right. Very nice job. Nice job, guys. All right. So far, so good. Okay. All right. So that one there, not too bad. Okay. Now the tough one here, I'll admit. Let's give the tough one a try. That's letter C. Okay, so letter C is, what is the probability of selecting a jury of 2 students and 3 faculty? Okay, in this case here, the probability of 2 students and 3 faculty. All right. Okay, now for us to figure this out here, one thing that's for sure, let's talk about at least the ground rules here. One thing that's for sure is the bottom part here is the same. Okay, so the 18 choose 5 is going to be exactly the same. That's still the total number of combinations that we need to test over. So nothing's going to change in that regard. You're fine there for the denominator. Okay, easy peasy. Really, of course, the tough part here in this problem is going to be the top part. So let's talk about that. We want to select 2 students here first and foremost for our jury. Well, once again, I ask the question here. How many students are there? And we're selecting 2 of them, right? So how could we write that? How many students do we have? And how can we write, again, taking a look at the number of students, and we're selecting 2 of them out of that pool. How could I express that here? That's close. Not 5 choose 2 here. Remember the pool of students here, Anna. So I am selecting 2 students, but 2 out of those 5 students are part of the jury. So I'm not actually doing 5 choose 2 here. Look at the pool of students instead of the pool of the jury. So you're very close with that answer. Just need to change one of those numbers. How many students do we have? Okay, there we go. Yeah, there we go. All right. All right, I like where this is going. All right, so correct, Horitz and Anna. The answer is 8 choose 2. Okay, so the answer definitely is 8 choose 2. So out of the 8 students we have in the pool, we're going to choose 2 of them to satisfy this probability here. We have to pick 2 students here that are going to appear on the jury. Now, the issue that comes after this is where people get most confused, and I do want to point this out here. So again, I'll guide you through this part of the process at the very least, and that is what happens after that part. And we have to choose 3 faculty. That part is true, okay? But what do we do in between 2 students and 3 faculty? Well, in fact, what you want to do is we effectively use the multiplication rule here again. So we are actually going to go ahead and multiply, all right? We're going to multiply here by 3 faculty here, which is, again, taking a look at the pool of faculty, which is 10. So we're going to have 10 choose 3. So we're going to have 8 choose 2 times 10 choose 3. I'm going to multiply those 2 together to figure out how many combinations to get 2 students and 3 faculty. All right, so before I move on here, are there any questions about that part in particular? Any questions why we went ahead and did multiplication there? Again, It's not addition, so I do want to point that out. That's why I want to say, hey, it's not addition, it's actually multiply. Okay, so let's multiply that out. Let's see what we get. I have no idea. So, take a look. Alright, so let's do it. 8, choose 2. And then we can multiply that by 10. Choose 3. Divide that by 18. Choose. So here we get 0.3922. Alright. Alright. Good stuff. Okay, any questions about that problem there? Okay. Good stuff. Alrighty. Easy peasy lemon squeezy. Okay. Alright, let's take a good look here at another one. Alright, this time though, we're going to look at the handout here, because we do have one more problem here from yeah. So that's just last one here. So let's look at number 5. Okay. What are the number of permutations with non-distinct items? So let's assume that each item here is non-distinct. Okay, we'll talk about what that means in just a second. So the number of permutations of n objects of which you have one of A of one kind, pardon me, B of a second kind, ... Z of a kth kind, is given to us by n factorial divided by A factorial times B factorial times ... times Z factorial, where n is equal to A plus B plus ... all the way to Z. So, this looks confusing, at least in terms of an abstract. I'm not gonna lie, it is rather confusing. Pretty. It's just like, okay, what exactly are we talking about? Well, that's why I put this down here, this example here, because I do want to actually make a distinguishment and say, okay, where you come up, what is a good example to kind of highlight what a non-distinct items mean. So an example here is if we have a flag of 3 colors. Let's say the flags are equally manufactured, but the only difference between those flags happen to be 3 colors. Okay, so we have green flag, a red flag, and a blue flag. And they're all the same dimensions, just the color is different. Okay, now let's say the flag can have different arrangements using these colors. Okay, so say we have 5 green, 3 red, and 7 blue. Okay, how many arrangements are possible of those 15 flags? So how many ways can we arrange 15 flags if we're given 5 green, 3 red, and 7 blue? And there's nothing to really distinguish each one of these types of flags apart from the color. Well, because we're not given distinct objects here, we're not given distinct objects outside of the color here, all right? They're all the same flags, they're all the same dimensions, they're all the same everything. We take our 15 factorial, which would maybe normally, okay, this is how we can arrange 15 flags, is 15 factorial if they're 15 separate flags. But since they're non-distinct items, since the only thing that's different between them is the color, we divide that by 5 factorial times 3 factorial times 7 factorial. And if you went ahead and did that here, you would have 360,360. All right. So that's how we can come up with that particular example. And is that, I hope that's okay, Juan. I moved it a little to the left there. So are there any questions about something akin to that? I wanted to be sure that you guys understood what do you mean by non-distinct items. Just like you have the same item, but the only difference is like color, but otherwise they're completely indistinguishable. Any questions about that? Hopefully that's pretty straightforward. So if you run into a situation like this, you're talking about the number of arrangements, and that's basically how we want to go ahead and approach that problem. Okay. All right. Easy peasy lemon squeezy. All right. All right. Questions? Questions. Okay. So that will take care of chapter 5 for the most part. Okay. Now, just to let you know, what is 5.6, by the way? I know this is all of section 5.5. 5.6, in a sense, is just basically a review section over everything in chapter 5. So, effectively, there's just going to be review problems from all the other sections. All right. So, again, it's just a nice little recap section here in section 5.6. So, it basically will go over the same things that we've talked about already up and through this chapter. All right. So, we're again doing pretty well here in terms of pacing and whatnot. So we're in really good shape. All right. Very good. Very good job here today, everybody. All right. Does anybody have any other questions before we head out for the day? Let's go back to the big board here. Oh, what happened to the music? I don't even know. It stopped. Oh, it did stop. I didn't even realize. All right. Okay. So I want to thank everybody here for coming on out here to the stream once again. All of you are absolutely fantastic people. We're gonna start chapter 6 here for next time, or we can also do a few more examples if you'd like for next time. Actually, why don't I ask you that right now? Do you guys want me to do a few more examples from this section or this chapter? I can do some review problems here from section 5.6 for next time if you think it will help. What do you guys think? What do you think I should do? I'll give you the option. Would you like to do a few more review problems, or would you like to move to chapter 6? Yes, more review? More review? Yes to what, Gally? Gally, you have to say more. Yes, please. Yes, more review? Okay, let me put a poll. I think I know what you guys are gonna say, but say, I was just gonna put that down really fast. Yeah, let's answer that here. I'm pretty sure I know what you guys want to say, but just to be sure on the safe side, I am not going absolutely bananas. Alright, so more review. Okay, well that's fine then. I don't have a problem with that. Okay, so what we're going to do here for next class is do some review problems from section 5-6. Alright, or again, anywhere from chapter 5, we'll do some more review, whatever the case may be, and we'll go ahead and do that. Alright, so that'll be on the docket here since that is what you asked for. Alright, well, thank you guys very much for your feedback. I really appreciate it, and we'll go ahead and do that for next time. Alright, everyone, have a wonderful afternoon/evening, and I hope to see you all same time, same place here on Thursday. Okay, so on Thursday, we'll come back here, same time, same place. Alright, everybody, take care of yourselves. Have a great one. I love you all. And as always, everybody, stay safe, stay healthy, but most importantly, stay sane. Have a great one, everyone. We will see you all later. Take care of yourselves. Have a wonderful night. See you later, everybody. All right. Bye. Bye, everybody. Thank you. Thank you. Thank you very much.